Okay, great. Hi, everyone, and welcome to our December Astronomy on Tap event. So welcome to tonight. It's our last event of the year in 2020. And thanks to everyone who is joining in with us now. Hopefully you're all saying hi in the chat to us now. We have two great speakers for you who are going to give two talks. And as always, we have our astronomy related quiz at the end. So I'll get started. So as always, we are here live on YouTube. Please do say hi to us in the chat. Let us know where you're coming from. For example, everyone who is currently in our Zoom chat room talking to you tonight and behind the scenes are coming from 5 different countries. So we're curious to see if everyone in our YouTube chat is as international as we're managing to be tonight. So please do let us know. And as always, we have our usual format of 2 talks of about 15 minutes long. Each of them will then have times for questions from you, our audience, afterwards. And then at the end, there's of course our quiz. And so please do stick around for that. So a little bit about Astronomy on Tap, in case this is your first time tuning into us. This is a global initiative and it was actually set up quite a few years ago. One of the first ones was in New York in 2013. And since then it has expanded massively across the globe. Usually it's about bringing astronomy to a relaxed setting like a pub or a venue in the evening. And so some of us are in time zones in the evening tonight. In fact, some of our speakers are in the US, so they're coming out to us during the day, which is great. But because of the global pandemic situation, this is our coronavirus safe version of Astronomy on Tap. And so you can get your own drinks at home for this one. So Astronomy on Tap is now active in 69 different cities across the world, 21 of which are in Europe, and we are one of those because we're Astronomy on Tap Gothenburg, usually based in Sweden. So who's here with you tonight? No surprises, I'm Holly Andrews. I've been your host for a few of these events now, and here I am again tonight. But we have many more people on our team. So that includes Kiana, who is going to be chatting to you guys in the YouTube chat and taking your questions from the chat and getting those to us so that we can then give them to our speakers. We've also got Andrew, who is in charge of our streaming tonight. And we have a group of Carmen, Sandra, and Paul, who all wrote our quiz. And tonight, Paul is going to be presenting the quiz to you all. We also have our speakers, Georgios and Eduardo. And we also have a couple other members who were involved with tonight's event and helping set everything up. So thanks also go to Franz, Iskra, and Jan for their help as well. And as always, I've already said you can talk to us in the chat, but in general, do feel free to like our videos, put notifications on, and subscribe to us to keep up to date on all of our events. Obviously, we've had a few events so far on our channel, and things are not going to be any different for at least early 2021. So please do keep an eye out on there. You can also find us on Facebook. We announce all of our events in advance on our Facebook page, Astronomy on Tap Gothenburg. But we also do tweet about it on Twitter with the same handle. And if you do have any questions or anything you want to ask us about and you don't get the chance to during our events, so say you won the quiz and you want to contact us, or if you just have questions about our events or had an extra question for our speakers, anything, you can email us at astronomyontap.gothenburg@gmail.com. So that's all the boring intro out of the way. I hope you're all still listening and you're excited for our talks. So the plan for tonight, we've got our two speakers as usual. So we'll be starting with Georgios, who's going to be speaking about space plasma instruments. So I will hand it over to him to do that talk. And then I hope you all have a good evening and you all have drinks, alcoholic, non-alcoholic, ready to go. So thank you. So Georgios, if you want to share your screen and then you can get started.
Yes, 1 second. Now you should be able to watch my screen.
Yeah, great.
So, okay, thank you. I'm really glad to have the opportunity to present some of my work in this nice event. So I'm Georgios Nicolaou, and I'm research scientist at Southwest Research Institute in San Antonio, Texas, United States. And my topic today is space plasma instruments, or as I call them, our eyes in space. So space plasma instruments are designed to measure plasma. So what is plasma in the first place? Why we care? Why we invest so much time and money to build them in order to study this plasma? So let me first say that the word plasma comes from the Greek word plasma, meaning multiple substance. In other words, it's something you can give a shape to it. It's interesting to tell you that in the Greek language, we actually use the word plasma to refer to humans. In nature, plasma consists of ionized atoms, neutrals, and electrons. And the plasma is macroscopically neutral, meaning that if you take a big sample of plasma particles, you will see that the positively charged ions are equal to the number of negatively charged electrons. And you will hear scientists referring to plasma usually as the fourth state of the matter, because plasma is not solid and it's not really fluid and does not behave really as a gas. Although we use fluid and gas models usually for simplicity to describe behavior of plasmas, the fact that they're so conductive, they carry electromagnetic fields, making the mechanism much more complicated, but believe me, much more interesting as well. So plasma consists the 99% of the observable universe. So it's everywhere and it's interacting with everything. on its way. You could see you could see new stars get born in dense plasma regions. You will see plasmas interacting with each other from the sun's solar wind plasma with comets and planets and so on. So as those interact with other bodies, they can interact with our planet as well. So investigating the plasma mechanism and understand how they behave, we don't just satisfy our curiosity, but it can give me useful tips how to protect our planet. And with the space instrumentation development, we have also technologically advanced that will improve our life quality in general. So in our neighborhood, the solar system, the main source of plasma is the sun. So charged particles and neutral particles are emitted continuously from the sun, propagating radially outwards with huge speeds. That's what we call the solar wind. The solar wind consists of fast particles with an average velocity about 500 kilometers per second. Sometimes they can exceed even 1,000 kilometers per second. These typical speeds are actually much, much larger than the speed of a fighter jet. And they interact with the planets and satellites or even astronauts on their way as they propagate outside in the outer solar system. And for example, in the picture up, you can see the sun emitting these fast particles, pushing the Earth's magnetic field, giving it to it this Medusa shape. And below, you can see that under some specific circumstances, the magnetic field lines of the Earth's magnetic field can break, and they eventually let these energetic particles to go through and get stored at the back, at the night side of the Earth. And with some other interesting mechanism, the magnetic field can get compressed and reconnect, pushing these high energy particles, guide them through the magnetic field lines of the Earth, and they can reach and penetrate the ionosphere, which they're going to cause these beautiful auroras that we all know. But this beautiful aurora actually underlines a very dynamical mechanism that it's sometimes harmful. So imagine these energetic particles reaching the altitude of airplanes, so they can penetrate the airplane and even the skin of passengers, which is really dangerous. Even though in some times they can have so much high energy that they can reach very close to the surface of the Earth. And if they interact with electricity production stations, they can cause major blackouts. And that would be extremely dangerous in cold cities up to in the north of the planet. So we need to study plasmas in order to protect ourselves. We need to understand how they behave. We need to monitor constantly solar wind that is heading towards Earth, for example. So in order to investigate plasmas in general, we build plasma instruments. And here I show 3 typical instruments on board some missions that I had the chance to work during my career so far. The first one is the Ion Composition Analyzer, or ICA for short, that is on board Rosetta. And ICA was resolving the ions in the environment of the comet 67P Churyumov-Gerasimenko. A similar design on a completely different mission is the solar wind around Pluto on board NASA's New Horizons mission. And this instrument is investigating the interaction of the solar wind with the far, far body, Pluto. And also we have the electron analyzer system on board Solar Orbiter, which is designed to measure solar wind electrons really, really close to the sun. So similar design, satisfying different science requirements in 3 different missions. One very far from the sun, one really close to the sun, and one around the comet. So you see that the typical plasma instrument is like this cylindrical metallic piece. Now I will make a cut through it to show a diagram to explain the measurement, the basic measurement principle. This is a typical instrument called electrostatic analyzer. There are many other types, which unfortunately I don't have the time to go through them. And I'm not expert in all of them, but I will use the electrostatic analyzer for the sake of this presentation. And here we have the aperture of the instrument where the charged particles will come through. So this is designed for charged particles. Here I will use electrons just for the demonstration. In the aperture, we have 2 metallic plates and we can apply a voltage difference between them by using a power supply to bend specific trajectories to come through. And then we have another metallic piece down here, which can also be set on voltage to bend the trajectories of specific energy per charge particles to go through. And eventually they're going to hit a position sensitive detector. And if I flip this detector now by 90 degrees to have a view from the top, you can see that I can split the position sensitive detector in different azimuth sectors to resolve the azimuth direction of the particle. So by playing with the voltage difference here and here and mapping the electrons, I can get their energy distribution and their direction distribution. And that's what every physicist wants to have in hand to analyze and get the properties of the plasmas. So I'm going to now refer to a very new, fresh European Space Agency's mission, the Solar Orbiter, which is carrying plasma instruments, but also many other cameras. It's going to picture the sun and at the same time study the plasma at the spacecraft location. Solar Orbiter will go very close to the sun. It's going to go to even less than the 1/3 of the distance between the sun and the Earth. At the same time, matching pictures that will take from the sun surface and matching with the properties of the plasma at the location of the spacecraft. And the plasma instruments will monitor the plasma distributions every 1 second. So every tick of a clock, we will know what the plasma is doing. And that is going to help us to understand where the plasma is actually originated, how it's accelerated, how it's heated, and eventually how it's governing the whole heliosphere, a big region around the sun that actually exceeds the trajectory, the orbit of the furthest planet. Here you see the spacecraft, so the entire Solar Orbiter spacecraft on a big vibrator. This is a vibration test. So the scientists and engineers, they vibrate the spacecraft to make sure that it can sustain all the vibrations we'll experience during the launch. So the launch was successful, and now we have the first data from this mission. And I personally work on the electron sensor instrument, the electron analyzer system, which I showed before. So some bits of my personal work. So I am modeling the response of this instrument, the electron sensor, in given solar wind conditions. So I simulate the plasma properties. Then I let my instrument model measure this plasma, and I simulate the observations. And then I analyze the simulated observations as I will actually analyze the real measurements. And then I compare the output of my analysis with the input I used to simulate the response in the first place. And then the comparison between input and output in my model, which can be just done in my laptop, can tell me how well the instrument can resolve different structures. So here you see input and output comparison of the plasma density, the velocity components, and temperature. And you see that there are regions that there is no 100% agreement. This tells me how good my method is in specific plasma parameters and what I need to reconsider analyzing better to get a 100% match. So it's a very important work to do the modeling. And here we apply the analysis tools to the real measurements. So those are really, really fresh measurements from Solar Orbiter. Those are electrons measured by the instrument I showed you before. So it's amount of electrons as a function of their energy and direction in both sensors and different frames. And here we apply the methods and we derive the plasma parameters, density, velocity components, and temperature. Different methods give you slightly or different results, but because of the models, we know why there is this deviation. So now we know what to reconsider, we know which range is optimal to be measured, and when it's not, we know how to treat and how to modify the methods to recover the actual plasma measurements from the observations. So yeah, modeling is really important to understand the instrument response, but the most important part, I will say, is the laboratory calibration. So before you fly your instrument in space, it's very wise and necessary to put it in the lab, in the laboratory, and simulate plasma conditions in space and see how it reacts. So you can then know what a measurement is actually meaning. So here is the calibration facility we have at Southwest Research Institute in San Antonio. You have a source of plasma coming from the right in this cylindrical tube. And here you have a small chamber that you can install instrument components in. And then this white is a bigger chamber you can put entire instrument inside and calibrate. And you can monitor everything through these computer monitors here. So as a student, I spent a lot of time myself in this exact desk, monitoring different experiments, studying how the plasma interacts with instrument components. And the funny fact, they told me that I was one of the few people that didn't really break any hardware in the lab. Fortunately, the last day before my graduation, I had an accident and I broke this telephone here. So yeah, that's my real contribution to hardware science, I guess. Finally, I would like to close and say that instrument science is really important. There is a huge effort all over the world from different institutes. They try to improve the plasma instruments, get better resolution, try to understand responses and build better instruments on top of that. And here are many missions. I had the chance to work during my 2 postdocs and my PhD. And I show also some landmarks from very beautiful places I have been working at so far. So yes, this is a cool business. And I really thank you for your time. And I'll be glad to answer questions.
Great, thank you so much for an awesome talk there. So we're going to give it a bit of time just for questions to come through from our chat because we do have a bit of delay. We are speaking to people on YouTube from the past, but I have a couple of questions myself that I wanted to ask, so I'll get the ball rolling.
Right.
One of those was this solar orbiter instrument is obviously quite close to the sun. And this is quite a harsh environment that close in, or at least my layman's view of solar physics is that that's the case. So I kind of had a question that's 2 questions. Is there an expected timescale over which the solar orbiter is going to be running? And also, were there certain aspects of the instrument where they had to take into account how to protect the instrument from this harsh environment? Obviously, you have to sense things, but you need to protect the rest of the instrument as well. So yes, that's my question.
I'm glad I had the design of the whole spacecraft here. So in the front, we have a big shield, a heat shield. So there's a material. I'm not really sure what consists of. But its job is to protect the instruments from sudden exposure to the sunlight because it will just fry them. And there are a lot of small holes that will just open for cameras to take pictures and some instruments to sample solar wind. And they can just close in case something goes wrong. Interestingly, though, our electron sensor is back in this boom. If you see the picture, I don't know if my mouse is really clear on the screen.
Yeah, we can see your picture on the Zoom channel.
Yeah,
so it'll be on YouTube as well.
So this box here, this electronic box with the 2 sensors, is actually mounted in this long antenna behind the spacecraft. So it's well in the shadow of the spacecraft. And actually, the specific instrument has to carry a blanket to keep it warm, although it's so close to the sun. But because of conductivity, the heat is not affecting if you put just a shield in front. So it's one of the big challenges of solar orbiter is the maneuvering, because you don't really want to make a small movement that will expose this instrument suddenly to the sunlight. And according to timescale, actually, I think the only thing that limits the operation of the instruments at this point is the telemetry. We don't really have an issue on the heating. I think we're well protected.
Okay, great. Thanks. We have had some questions come in. So we've had a question from MCTP. And the question is, do the observations really match what was expected from the simulations of solar events?
It's very early at this point to say where these models I showed are the preliminary. So what I do at the moment, I put by hand what I expect the solar wind to be, and I show that the models can reproduce these, so the instrument can resolve the structures that I expect. We didn't really analyze electron data yet. Just the small part I analyzed, yes, I can say that the densities we're seeing, that we're deriving, are pretty much in the order of what we expected. Of course, we want to be surprised and see structures that we don't expect. But from the little bit of data I have personally analyzed, I will say that so far, we have expected average parameters. We didn't go to details yet, but I'm sure we have specific operation modes that will sample really fast, really short-lived structures. And that would be the amazing science to be done with solar orbiters.
Great. I'm just going to give it a couple of minutes to wait for some more questions. Oh, I think one is coming through now. So just while I'm waiting for that to come through, I was going to ask another question of mine. So you mentioned that you have these different plasma detectors in space, both ones as close as solar orbiter, but also ones as far out as Pluto. So I wondered, how much of an impact does that have on the instruments that you have to develop, depending on how far from the sun they are?
In terms of geometrical design, which I am the one who is, I'm designing parts of that. As part of the design, not really. You can actually copy one instrument that operates in Pluto and put it really close to Earth. That's actually been done. It's a NASA's mission called IMAP. They're using almost same design that they used in Pluto before. Now, in terms of spacecraft shielding, yeah, this changed the picture, but not the actual instrument itself, I would say, although I'm not really expert on this design for heat shield. But as concerns the instrument geometry, no big impact on that.
Okay, great. And so we've had another question come through. So this one is, what do you think is the most exciting discovery that could be made from this new instrument? And this one is from Kiana.
Yes, the instrument, well, the mission is new and the operations are quite fast. So we're going to resolve small scale structures, which means in terms of physics, before we could, for example, monitor plasma every minute or just few seconds. Now we're going to exactly a second, or we have operations that are going to resolve plasmas even in sub-second scales. That will give you really cool information about how the plasma is exchanging heat with the surroundings, if it's absorbing heat, and where is it getting it from. For example, we know that the solar corona is hotter than expected. It's even hotter than the structures of the sun below. How is this happening? So maybe now solar orbiter with the cool pictures and at the same time monitoring the plasma with this type of instruments will tell us what mechanism is hitting the plasma. We don't know yet. So that's one of the cool parts we can see. Hopefully soon.
Great. And I think we've just had another question through now from Anders Carl. So I think this might be our last question, but please do keep asking them in the chat if you are watching. And this question is, what is the resolution of this instrument? Is it needed to move the instrument to cover the entire surface of the sun?
No. So this is a 3-axis stabilized, so it can be stable. And through the voltage scanning, we can sample the entire sky. So we don't need to spin the instrument around to take full coverage. So this clever mounting on the spacecraft box, so you see the orthogonal mounting. So the two sensors can complement each other in terms of coverage. But here, these metallic plates are on voltage that is fastly changing in order to sample different directions. So you can sample the entire sky with not moving at all your instrument, just changing voltage between these plates. It takes some time to go through the voltages. And that's the 1 second limitation we have. Because the plasma flux is not infinity, right? You have to wait some time to get enough particles to do some statistics. And to scan through all the directions, it takes some time. So about resolution, we resolved a couple of degrees in each direction. And in terms of energy, about 10% of each energy step we can resolve. So each energy step is 10% from the mean value from each other. And in terms of time, it's about a second.
Okay. I'm just going to squeeze in another question. This one is from Linnea, and this is, how has the amount of plasma changed in the universe over time?
Very interesting. A little bit more general, though. Well, I think in our solar system, yes, we have decreased a lot the flux of the plasma, but I can just refer to a few papers that deal with it because I personally don't. But there are papers studying, for example, ancient sun conditions when there is an explosive event. They consider that sampling what was going on many years ago when the solar wind flux was much, much more. So if I consider an explosive event carrying 10 times the mass of a typical solar wind and 3 times faster, then I would say that's roughly the order of less flux we're getting now from some point in the early solar system era, which was, I guess, billion years ago. But
Great.
yes, there are a lot of papers that they can give you much more expert opinion on that.
Okay, and we just had a follow-on from the earlier question about resolution. So you talked a bit about temporal resolution or resolution over time being about a second, but they were just wondering about the physical resolution in meters. So each of your samples that you take by looking at different voltages, does that map to a specific physical space on the sun or physical resolution?
Yes, so that's a very interesting question in terms of physics as well. So this plasma is flowing with, as I said, around an average distance of 5 kilometers per second, 500 kilometers per second. So imagine that 1 second we need to sample it, that move 500 kilometers apart. Unfortunately, we have to consider that there is some isotropy, some uniformity of the plasma we're measuring in this small amount of time, but it's actually not small, it's 500 kilometers. So we have to go with that at the moment. The only way to overcome that, and it has been done before, for example, in the Earth's magnetosphere, if you have heard of the spacecraft Themis, Cluster, or MMS, there are multiple spacecraft in different locations. So there you can resolve the structures in space. With one spacecraft measurement, you have to go with that fact that your structure is passing your spacecraft in this time. We can combine measurements from Solar Orbiter and some of few other spacecrafts in the neighborhood, but we will not beat these few tens of kilometers for sure.
Okay, thanks so much for answering all these questions. So I don't think we have any more for the moment, but as I've said, if you are watching us on YouTube tonight, please do feel free to ask more questions, and we can see if we have time after our second talk and after our second speaker has answered questions to go back if we do miss any. But for now, we're going to take a short 5-minute break. So feel free to take a bathroom break, go to the drink, and we'll be back with our second talk after that break. Thanks. Okay, great. So thanks to everyone who is stuck around after the break, and I hope that you are all back now. So we're now going to have our second talk of the evening, which is about clumps from distant galaxies, and this is by Eduardo. So Eduardo, I'm going to stop sharing my screen, and if you can feel free to share yours and get started.
Yeah, perfect. Thank you. So let's check if it works properly. Can you see it?
Yes, great.
Okay, perfect. So good evening to everybody. Thank you for having me here. I'm Eduardo Jani, and I'm a postdoctoral researcher at the Kaptein Institute of Groningen, the Netherlands. And this evening, I will introduce you to what I believe is a very fascinating field of the astronomical research, that is the study of distant galaxies. And in particular, as you can see from the title of my talk, I will mostly focus on a very specific type of galaxies that are galaxies hosting so-called clumps. However, before getting started, allow me to spend a few slides describing what a galaxy is, just to be sure that everybody that is listening to us is on the same page. So a galaxy is a very complex system, and generally is a gravitationally bound system made of mainly stars in different evolutionary stages. So we go from very young stellar objects down to the final product of stellar evolution. In particular, I'm referring to black holes, neutron stars, white dwarfs. Then we have the interstellar medium that is composed of both gas, mainly hydrogen, in different phases. So we can have it as molecular gas, neutral gas, ionized gas, and also dust. And finally, last but not least, we have dark matter. That is this big open question mark in modern cosmology that has a fundamental role in the formation and evolution of galaxies. Now, these four components have to be taken into account as real ingredients. So it's like we're cooking a galaxy. So these are fundamental components, fundamental ingredients, but of course, each one of these ingredients can be slightly, the percentage of each ingredient can be slightly changed. And if we do so, we end up cooking very different kind of galaxies. So if we look in the universe to galaxies, well, we can find that they differ for many aspects. For example, they differ in size, they differ in mass, in luminosity, and also in shape. And here I'm just showing you a few examples on the right-hand side of this slide. Now, in the following, I will mostly focus on a specific class of galaxies that are so-called star-forming galaxies. And as you can guess from their name, these are galaxies that are currently undergoing some phenomena that allows to form stars from gas. And to do so, it's absolutely necessary that these galaxies have a huge amount of gas. So they have to be gas-rich. So let's have a look at a few of these galaxies in what is the local universe. This is a region around us of about 1 billion light years in radius. So it's already a mind-blowing, at least to me, it's already a mind-blowing distance. And here you can see a few examples, a few shapes of these star-forming galaxies. And as you can see, these galaxies appears to be rather regular, to have a rather regular morphology, a smooth shape. And it's mostly composed of two main constituents. So a disk, sometimes this disk has also spiral arms, but not always, it's not a mandatory thing. And where you can find very young stars, dust, and gas, and a thicker region towards the very center of the galaxy that is the so-called bulge, where you usually find older stellar populations together with gas and dust. Now, we can wonder and ask ourselves if this kind of shape has always been in place, also in the very early stages of galaxy formation and evolution, so in the very early stages of the universe. to do so, we can start looking at galaxies in the distant universe. So now I'm starting considering galaxies, star-forming galaxies that are at a distance of more than 1 billion light years from us. And as you can see here, I'm just showing you a few examples. Well, the situation is dramatically different from the previous one. So here, the galaxies appears to have a regular morphology that is dominated by bright concentrations of lights that are the so-called clumps. And as a consequence of the presence of these clumps in these galaxies have been dubbed as clumpy galaxies. Okay, so as you may know, well, light, when propagates in a medium or everywhere actually, it has a finite speed. So it needs some time to go from point A to point B. This means that when we start looking at something that is distant from us in the universe, we're not just talking about distance in space, but also distance in time. As a matter of fact, the light that we're detecting from these galaxies that we're just observing with our telescopes right now left the galaxy more than 1 billion light years ago. 1 billion years, sorry, 1 billion years ago. So in a certain sense, we can think that if we start looking at star-forming galaxies at different distances, actually we're kind of tracing how the shape of the evolution and also their properties changed with cosmic time. So now we can ask ourselves, okay, what is the mechanism? There has to be a mechanism that brought galaxies from having a clumpy morphology to something that is more disk-like, so something that is more regular, and then we can observe in our local universe. So simulations have shown that this process is mostly driven by the fusion of galaxies. In particular, here I'm showing you simulations. And with the fusion of galaxies, I refer to the process of mergers. So when two or more galaxies meet each other and they blend together. But we can also ask ourselves, is this the only process that, let's say, can bring galaxies from having a clumpy morphology, clumpy structure, to something that is more disk-like and has a bulge? Is there any other process that maybe is not affected by and is not related to the environment of the galaxy and to the interaction with the other galaxies? So, well, of course, we think we have another option that is related to the clumps. But first of all, to answer this question, we have to understand what clumps are. And indeed, this is quite a debated issue in the astronomical community. So the astronomical community is split between those who believe that clumps are just the effect, the consequence of an inhomogeneous dust distribution within galaxies, and those who believe that clumps are giant star-forming regions. So they are real structures within the galaxies. So let's go through these two scenarios very rapidly. So let's start from the dust distribution. So to fully understand this kind of a hypothesis, we need to characterize the dust and its properties. And it's something very difficult to do. So to make it easy here, allow me just to, let's say, state that dust can be considered as a screen in general. So if you have a source, a light emitting source, and in between you, the observer, and this source, there is some dust, well, the dust will, let's say, absorb part of the light that has been emitted by the source. And so in particular, if there is a lot of dust in between you and this emitting source, well, you can also end up with not being able to detect the source at all. So in galaxies, of course, the distribution of dust is not something homogeneous. So we have regions where you can find a lot of dust, regions where there is none. And so we can think to dust as a worn out, shabby screen with holes in it, and with the regions where the screen has thicker fibers and thinner fibers. So it's something irregular. And the consequence, the net effect of this dust screen is that a homogeneous and and smooth light emission coming from stars, for example, can be observed as patchy, and in particular that clumpy. The second scenario is actually that these, as I already said, these clumps are giant star forming regions. And to, let's say, allow you to grasp a little bit what I mean with this, I'm showing you here two different images. One on the right-hand side is always for our clumpy galaxy in the distant universe. On the left-hand side, this time we have a UV image of a local galaxy, in particular a rather famous one, that is the Whirlpool galaxy. So I hope you can see that there are a few similarities between these two galaxies, and I'm referring to clumps. As a matter of fact, also for the Whirlpool galaxies, you are able to detect the presence of these bright concentrations of light. I just want to underline that I use the term ultraviolet image because in general, when we take a picture of a galaxy in the ultraviolet, we are actually looking at the distribution of very young stars, very hot and young stars. So these crowded regions of newborn stars are actually really the cradle, the nurseries of newborn stars. So they're star-forming regions. And why we are referring to clumps in distant galaxies as giant star-forming regions, because, well, when we start measuring the sizes of these clumps in distant galaxies, their mass, it's much, much higher than what we can usually find in local galaxies. So if we can take into account that clumps can be star-forming regions, how do they impact to the galaxy structure? And to understand this, we have to understand what is the fate of clumps. As I already said, also at the very beginning of this talk, in general, well, clumps to form stars, they need to be rich in gas. So clumps are very gas-rich regions of a galaxy. Now, during the evolution of a star, there are a few stages, in particular towards the end of the stellar evolution, that are particularly energetic and are able to, let's say, sweep away, to blow away all the material, that's all the interstellar medium, the gas that is surrounding a star. And so you can understand that then, if we start thinking about our clumps, these clumps are forming many, many stars at the same time. So they, with time, they will evolve and they will go through these stages that I think most of you have already heard about once, at least in their lifetime. If you're interested in astronomy, that are supernovae explosions and stellar winds, for example. A little bit, let's say, stronger stellar winds than the ones we were talking before. And so with time, we do expect that this phenomena will expel a huge amount of gas from our clumps, and this will bring to an end of the star formation activity of our clump. So, well, which are the scenarios? Simulations tells us that there are two different scenarios. The first one is that clumps are short-living structures. So they are not able to survive to these phenomena, to supernovae, for more than 50 million years. So that is already a huge amount of time. But it's, of course, a blink of a cosmic eye. And in this case, of course, clumps are just transient features of galaxies. They form, they evolve, and die almost in the same location where they form. So there is no impact on galaxy structures. What happens if their lifetime is longer? So if they can survive more than 50 million years, well, the situation is dramatically different. Here, I'm just drawn a very simple sketch at the bottom of this slide. You have a time arrow at the very bottom, just describing you how things evolve with time. The idea is that the clumps have enough time to move within the galaxy, to migrate inwards towards the very center of the galaxy, where they blend together, they fuse, they merge, and they help constituting, or they form, really form the bulge, that structure, the thicker structure we saw at the very beginning. So my personal research is mostly focused right now on this aspect. So I'm trying to find some observational evidence some estimates on how fast gas is expelled from these clumps to understand if this can be considered as an alternative, an additional scenario to the galaxy merger that I described to you before. And I think that my time is up, I suppose. So I will wrap it here, and I will thank you for your attention, and I'm glad to say answer to all of your questions.
Thank you so much for an awesome talk. So we do have one question so far, and to everyone who is putting questions in the chat, please do. Obviously, as before, we are delayed by about 30 seconds, but we will get to your questions. So this first question is from MCTP, and the question is, how do you know that all of the clumps that you see in these galaxies are linked or have the same sort of origin?
So can you repeat? Sorry.
Sure. The question is, how do you know that all of the clumps are linked?
Oh, you mean that they're not something in foreground, something like that?
So I think the way that I would interpret this question is, as in, do all of these clumps have the same sort of explanation within that galaxy?
Well, I would say it's a little bit difficult. As I said, there is kind of, the debate going on about their nature. So it's not 100% sure if they're real physical structures or not. If for those who knows a little bit maybe more about astronomy, something can maybe be said from studying the infrared emission of these galaxies. So if you start detecting and let's say probing the extent and position of dust within a galaxy, that is something you can do. Well, then you can try to discriminate actually between these two scenarios. Otherwise, it's a little bit difficult. It's true, if this is answering actually the question. Otherwise, I'm not sure if it's more referred to the fact that these clumps are linked to the same galaxy. I'm not so sure. So
yeah, so we've had a clarification.
Okay,
the question is, are these clumps not superposition? So I think it might be what you were asking.
That is an extremely good question, actually. And here I'm showing you just a few things. I suppose that what can explain answer to this question is actually the two panels on the top right. So here you can see a simulation of a galaxy with different resolutions. And of course, so it's absolutely the same galaxy, while on top we have a resolution, a very high resolution, spatial resolution of about 3 parsecs. And below, I think, sorry, I have all the faces here, so I'm not sure I can read, but I suppose it's 1 kiloparsec or 500 parsecs, I'm not sure, but it's written there. So, and you can see dramatically that depending on the quality and the special resolution that the current instrumentation can reach, well, it's not necessarily true that they're giant star-forming regions. And of course, you could have some superposition between two different clumps. So there's a lot to do in this regard. And this is one of the reasons why I think it's a fascinating field. I hope that now with the next future facilities like JWST, we will be able to go a little bit even more into the details of these structures. But yeah, so we are for sure hampered by the special resolution that can be achieved here.
Yeah. Our next question is from our Peter. So it's a great presentation, and I would agree with that comment. The question is, are there any other hypotheses / theories other than these clumps and galaxy mergers to explain how these galaxies evolve, changing from the shapes that you see there to shapes of galaxies that are more similar to what we have today or in the local universe?
Yeah, I would say that right now the most credited one is the galaxy-galaxy merger, but actually we also can take into account some phenomena that of star formation that is taking place outside of the disk and maybe along possibly filaments that are refueling of gas the galaxy itself. So there is, of course, this other option here that is taking place. And so you have some gas that from the surrounding of the star, of the galaxy, sorry, it's refueling it. And within this filamentary structure, so you can start having some star formation, and that could explain, could be an additional explanation for the presence of a bulge.
Okay, great. And we've had another question from Paul, and that is just curious if these clumps are positioned towards a particular part of the galaxies or within the galaxies. Do these clumpy properties vary among different galaxy types?
Oof, well, let's say I'm particularly studying high redshift, distant galaxies. So it's a little bit difficult to actually see sometimes. As you have seen before in the image, it's difficult to define maybe also the center of a galaxy. It's a tough question to answer. I don't think we see specifically in the distant universe, we don't have any tools to discriminate if they form specifically in one specific regions of the galaxy. Here, as you have seen before in the Whirlpool galaxy, as you can see, these clumps are along the spiral of arms. So where you have let's say, gravitational wave, the shock waves that compresses the gas and allow to start the formation of stars from the gas. So yes, in this case, you can see there is kind of a well-defined distribution, but for distant galaxies, it's too difficult to say.
Okay, so there's a lot of open questions. I'm just going to give it another minute for questions. So I'm going to ask one question that I had. I very much don't know anything about galactic evolution. You talk about the local universe being the closest billion years, whereas I work with stuff in our galaxy. But so you talked a bit about both these clumps and the mergers being what can evolve these galaxies from these very different shapes to shapes that we see today. I was wondering, are these also possibly evidence of galaxies undergoing mergers already, or do we expect that to only happen post these more clumpy structures that you're seeing?
Oh, no, sure. It could be that we are also witnessing some merger phenomena in here. So in a few of these galaxies here, that can happen. Actually, you can see mergers also at high in the distant universe. It's not necessarily something that is mostly related to the local one, not only. But yeah, so I would say that it's a phenomenon that you can see on very different distances in time, let's say. Allow me to use this, or otherwise at different redshifts. Yeah.
Okay, great. So we've not had any more questions through. We do have Franca in the chat just wanted to say thank you for your interesting and clear presentation. So I thought I'd let you know we had that feedback. But now we're probably going to stop, and I want to take this opportunity to thank both of our speakers for some really interesting and clear presentations tonight. Both gave a very good introduction and then went into some interesting and exciting detail on both of the topics. So I wanted to thank you both for joining us on Astronomy on Tap Gothenburg tonight. But for now, you can relax, although if you want to take part in our quiz, please do. So next will be our quiz. So I'm going to pause for a minute, and then we will be handing over to Paul in about a minute for the quiz to start. So everyone at home, please do stick with us, and we will be starting our quiz. I'm just going to give 30 seconds in case anyone needs it. Okay, and so now we are going to get started on our quiz. Just a little bit of introduction to anyone at home is watching us for the first time tonight. Just to let you know, there is a delay between us and you guys on YouTube, but please do join the quiz. We will be posting a link in the chat via our chat moderator for tonight, Kiana. She will be sending you guys a link to our Google form. And then Paul is going to talk us through the quiz. And then after that, there'll be a minute or two for you guys to finish off any of your responses. And then when everyone is done, we will announce our winners, both our astronomy winner of the evening and our team without astronomers. And as always, if you do win, then hopefully once we are back to hosting in a physical venue, we can get prizes to our quiz winners. Or if you're joining us from abroad, maybe we can start figuring out another way to get prizes to you. But yeah, so I'm now going to hand over to Paul. So Paul, you're currently muted. Yep, brilliant.
Yep, so hope you guys are seeing the screen right now. So here we go to be the last of the Astronomy on Tape quiz of this year. So we'll start by you can just fill in your team name here, and just to indicate if you are an astronomer or if you have any astronomer on your team, so just choose it here, yes or no. And I will start reading off the questions now from question by questions, but just also reminded that there will be some delay between the YouTube and here. So just bear with us as well. So let us get started. So the first question is, which of the following mediums may be considered as a plasma? So the first one on top left is interstellar medium. And then the second is jet outflow from active galactic nuclear, or solar wind, or finally, all of the above are considered as plasma. For the second question is, which of the following statements is not correct? So first statement is plasma is one of the 4 fundamental states of matter. The second statement is charged particles are essential components of plasma. The third statement is plasma can only be found to occur outside of the Earth's atmosphere. And the last one is all of the above statements are false. So which one is not correct? So the third question is, which of these observable phenomena is due to the effects of plasma? So the first one is aurora. The second is sundog effect. The third one is the sky being blue in color. The fourth is green flash effect. And finally is all of the above. So the fourth question is, which of the following telescopes is the first to be equipped with a plasma detector on board? So the first is Voyager 1. The second is Rosetta. The third one is Juno. And finally is Webb. So the fifth question is, which of the following astronomical phenomena occurs as a result of interaction with plasma? So the first one is Faraday rotation effect. The second one is synchrotron radiation. The third one is bipolar diffusion. And finally is all of the above. Question 6 is, what is the temperature range of a plasma? So the first one is 0.1 Kelvin to around 300 Kelvin. The second is 10 Kelvin to around 100 million Kelvin. The third one is about 1000 Kelvin to around 100,000 Kelvin. And the final option is 500 Kelvin to 500,000 Kelvin. So the next question is, what is an Einstein quotient ring? The first one is a special toroidal structure of plasma around stars. Or if it is when a lensed galaxy has a ring-like structure, or a porous galactic clump larger than 40 solar masses. Or finally, would it be when the lensing galaxy has a ring-like structure around it due to outflows? So which one do you think it is? So then the next question is then, which famous radio telescope collapsed recently in 2020? So the first one is Submillimeter Array, or known as SMA. The second one is Arecibo Observatory. The third one is Caltech Submillimeter Observatory, or known as CSO. Or the last one is Very Large Telescope, or known as VLT. So the next question is then, which of the following statement is correct? So the first statement is gravitational lensing cannot allow astronomers to identify distant galaxies. Well, actually, gravitational lensing is one of the main techniques to identify distant galaxies. Or galaxy clusters are only composed of galaxies like our Milky Way. Or none of the above are actually correct. So the next question is, identify the image not presenting gravitational lens effect. So it's just they show these figures if they are actually having this effect or not. Or actually all image present gravitational lens effect. Then question 11 is, which of the following is not a solar science observatory? So it's Usis, Juno, Aditya, or Soho. Now, question 12, which of the following about the solar wind is correct? So the first one is the solar wind is mainly composed of a stream of electrons and protons. The second one is the temperature of solar wind can reach about 1 million degrees Celsius. The third one is the solar wind is responsible for the creation of the observed tail of comets. Or the origin of the solar wind is the hot corona of the sun. Or finally, if all of the above are actually correct. The next question is, what is the cosmic snake? So which is shown in this image. So is it a star-forming molecular cloud? Or if it is a giant cosmic filament? Or actually it is a lensed distant galaxy? Or actually it's a lensed distant galaxy clusters, which is composed of many galaxies. So now the next question is then, what does a blue color associate with clumpy structures in galaxies indicate? So it is a recent supernova, or it is a signal of magnetic field activity, or it is a wind-wind interaction between massive stars, or finally it actually represents star formation activity. So which one do you think it is? Now, for question 15, you're gonna first watch this video or hear this track. Oops. Maybe it's a little bit trying to zoom in. So based on this track, the question is follow. We hear different kind of tones with short and long. So what do the short and long tones in the video represent? So actually this is a sonification of an astronomical image. So you're actually converting image into some sort of sound according to the structure in the image. So the short tones is neutron star and the long tone is white dwarf, or the short tones is cosmic microwave background radiations, while the long tones are black holes. Or the short tones is stars and the long tones is galaxies. Or if the short tones is star, but the long tones are molecular clouds. Or finally, the short tones are supernova and the long tones are neutron stars. Now, the next question is, which of the following made headlines in 2020? So the first one is detection of gravitational waves, or actually receiving the first confirmed signal of an alien civilization, or the observing B-mode polarization due to primordial gravitational waves, or actually a Nobel Prize awarded to researchers related to black hole science, so which actually made the astronomical headlines this year. So now a final question is, how fast does Santa's slide have to travel to bring presents around the globe? So would he have to travel in 10% of the speed of light? Or he has to travel in 90% of the speed of light? Or he has to travel in 0.1%? Or even finally the 0.5% of speed of light? So now I think you give also a brief moment because of the delay so that you may fill out the answers. Okay. So we are going to show the answer in a very short moment. So I'll probably give another minute if you are going to have a final answer and you submit the quiz. So after 1 minute, then we will start going through the quiz and show the answer as well. Okay, so I think it's a minute and we are starting to go through the answer now for the quiz. So the first question is, which of the following mediums may be considered as a plasma? And actually correct answer is all of the above are actually considered as plasma. So there's a lot of people actually answering correctly. So the second question is, which of the following statement is not correct? So actually the statement is not correct, is plasma can only be found to occur outside of the Earth's atmosphere. So actually ionosphere is one of the Earth's atmosphere consists of plasma. So the next question is, which of these observable phenomena is due to effects of plasma? And of course it's aurora, as mentioned in the first talk. So it's due to the interaction between the solar winds and the Earth magnetic field. So the next question is, which of the following telescope is the first to be equipped with a plasma detector on board? And actually, interestingly, the first telescope is Voyager 1. So actually they equip a Faraday cup on top of the instrument to measure the solar wind properties. So actually it is the first observatory. So the next question is, which of the following astronomical phenomena occur as a result of interactions with plasma? So actually all of them are correct. So the next question is, what is the temperature range of a plasma? So actually the correct answer is from 10 Kelvin to 100 million Kelvin. So actually it's a very wide range. And the next question is, what is an Einstein-Croson ring? So actually the ring is a lensed galaxy, has a ring-like, this is a kind of a lensed galaxy and form a ring-like structure when it's observed. So the next question is, which famous radio telescope collapsed recently in 2020? Yes, and actually it's Arecibo Observatory. And the next question is, which of the following statement is correct? And the correct statement actually is the gravitational lensing is one of the main techniques to identify distant galaxy because of the optical effects. So the next question is, identify the image not presenting gravitational lens effects. So actually all images are presenting gravitational lens effects. So it's really amazing that this effect can form different shape, like ring and arc-like and etc. So next question, which of the following is not a solar science observatory? Yep, actually it's Juno. So the other three are actually solar telescope coming from different time. So the next question, which of the following about the solar wind is correct? And actually all of the statements mentioned are correct. And next question, what is the cosmic snake? So the cosmic snake actually is a lensed distant galaxy. And interestingly, you have a multiple image of the same galaxy, of some part of this galaxy, actually all kind of overlaid, and then with a strongly magnified to form this cosmic snake. And the next question is, what does a blue color associated with Pumpy substructure in galaxy indicate? So actually this color represents star formation activities. So the next question is, what do the short and long tones in the video represent? So actually the short tones are actually stars, and the long tones are actually representing the galaxies. So which of the following made headlines in 2020? So actually it's Nobel Prize awarded to researchers related to black hole science. And then the final question is, how fast does Santa's have to travel to bring presents around the globe? Actually, there's a study by Lancaster University, and they actually trying to measure that, and they found that you need to travel in 0.5% of the speed of light. But nonetheless, this is actually a question that I would think that is just for Christmas time. And so everyone, it doesn't matter which answer is right or wrong. But just Merry Christmas, and hope you guys are going to enjoy the quiz and the astronomy on tape. So yeah, I will also pass back the time to the MC as well.
Okay, great. So I also just wanted to sign off the quiz part of our chat by announcing that Keeks and Oskriko won, who were the astronomers that won. So very well done from both of you. That was tied with 15 out of 17 points. And for non-astronomers, it was Val, Coping, Astro, and the Lone Mum with 13 out of 17 points. So not too far behind. Very well done there as well. So I just want to sign off for all of you tonight. And I just want to say, stay tuned for our next event. I hope you all had a good year. It's been a strange one, but hopefully you've enjoyed coming along to our Astronomy on Tap events, both physically at the start of the year, but also our digital ones that we've had throughout the year. And this is very much not the end for us. We will be back again in early 2021. We already have confirmed speakers that we're excited to start posting online to tell you more about, but we'll be back with you in late January with our next event. So thank you all very much and have a good evening.